We're about to start the session. Now, as I announced previously, unfortunately, George Fuller was not able to come due to illness, but he is brave enough to give his talk over the telephone. So let's all please be patient and help him get through this, because it's a very interesting talk. Okay, now before we start, I want to repeat the announcement I made before about the buses. There will be at least one bus leaving at the end of this session. In the previous slide it said 5:30, but that was a mistake. It's actually going to leave at the end of this session, which is scheduled to finish at 5:45. Okay, so it'll leave between 5:45 and 6. So if you don't want to stay for the public session, please, at the end of this session, go out. There will be a bus there for you. Okay, let's just make a check of the sound here. George, would you be so kind as to say something so that we can verify there is sound on the microphone?
I'm here.
Okay, we can hear you. So I think we can get started, basically. So I will flip through the slide every time you tell me, George, okay? We are now on the opening slide with the title on it.
Okay, so I'm going to talk about the CMB and new neutrino physics and constraints on new neutrino physics and the promise of constraints on new neutrino physics. I thank the organizers for inviting me to give this talk. I'm very sorry I'm not there. I came down with the flu last week and I felt pretty lousy. I'm glad I didn't get on an airplane actually, but I'm feeling a bit better now. So next slide, please.
Okay. Okay, it's on.
Okay, so I think we have a very exciting future developing in neutrino physics and neutrino astrophysics, really for three reasons. Because we have these comprehensive microwave background measurements that we'll discuss here, of course, and you have been discussing. Of course, measuring the cosmological parameters, measuring the radiation energy density, with the promise of interesting, totally independent new constraints on the primordial helium-4 abundance, and of course neutrino mass limits, which are really limits on the collisionless damping scale of neutrinos, essentially the free streaming. Plus we have this revolution going on in optical astronomy. I said 10 and 30 meter class telescopes in the future, adaptive optics, other technologies. And so for us and for neutrinos, what that means is essentially precision measurements of the deuterium abundance. They'll get better in the future. And that is actually quite significant for constraining neutrino physics. And then finally, it's the neutrino experimental measurements that have been made in the last 10 years, which are really pretty amazing. So I think all of this is setting up a nearly overdetermined situation. If there's new beyond standard model physics in neutrinos, I think it will show itself. Next slide, please.
Okay.
Okay, so this is what we know and what we don't know about neutrinos. So we know the mass squared differences, the differences of the squares of the vacuum neutrino mass eigenvalues. Because we know the mass square differences of the solar neutrinos as shown and the atmospheric neutrinos, but it's significant what we don't know. We don't know the absolute masses of the neutrinos, although we know we have masses, and we don't even know the arrangement of those masses. So we don't know the mass hierarchy, which are shown, the normal mass hierarchy where the atmospheric doublet is on top, and there's one heavy mass eigenvalue, and the inverted mass hierarchy where it's the other way around, the solar doublet's on top. Next slide, please.
Done.
Okay, so a takeaway message of the experiments, however, is that the weak interaction eigenstates of the neutrinos, the so-called flavor states, are not the same as the energy or mass states, the propagation states of the neutrinos, which are 1, 2, and 3 there. And of course, there's some unitary transformation between these bases, and there are 4 parameters there that characterize that transformation, 3 mixing angles and a CP violating phase. And as of last summer with Diab, we've actually measured all the mixing angles. 10 years ago, this was kind of a holy grail of particle physics, and now we've got these, we've got most of that parameter space. And moreover, the theta 1-3, that angle that was missing until last summer, is large enough. It's actually larger than even the astrophysicists thought it would be. And it's large enough that it sets up the possibility of being able to constrain or even measure the CP violating phase in long baseline experiments, for example. Next slide, please.
Okay.
Okay, so armed with what we know about neutrinos and their interactions, it's pretty simple to figure out in the standard cosmological model what happens. So ordinary active neutrinos will decouple at a temperature scale that's of order 1 million electron volts, about 1 second in the age of the universe. And you know the story. When the neutrinos are decoupled, they're decoupled. They don't share in the thermal energy of the plasma anymore, so that as the universe expands and in equilibrium, the electron-positron pairs go away, the entropy that the pairs carried gets transferred to the photons of the plasma, but not to the decoupled neutrinos. And the net result is the neutrinos are refrigerated relative to the photons by something like 40% in temperature. So, of course, we measure the photon temperature. We don't know whether the relic background is there or not. Actually, we know it's there at the time of Big Bang nucleosynthesis. If it wasn't, we wouldn't get the right light element abundances. But the question is what happens to it afterwards. Next slide, please. So, if here's a cartoon, the cartoon that we all know and love. There are something like 410 photons per cubic centimeter in the relic background. So from what I just showed you with, kind of relativistic kinematics, Fermi-Dirac blackbody energy spectra for each of the 6 kinds of neutrinos, nu E, nu E bar, nu mu, nu mu bar, nu tau bar, there should be something like 300 of those per cubic centimeter. And if I think about the causal horizon size, that's roughly 10 to the 87 neutrinos inside the causal horizon, which is a fairly big number. And if you multiply that by even a small rest mass, like an electron volt or something, then you get a dynamically important mass. So that's very interesting. Next slide, please. So it sets up the possibility that you can actually measure this mass. So one cautionary note, however, the CMB and large-scale structure do not actually measure the neutrino rest mass, but rather something like, for lack of a better word, a convolution of that rest mass with the relic neutrino energy spectrum. So what's really relevant is how far that neutrino moves at a given time. So let me turn this problem around a little bit. What I showed you is we know the mass square differences. Unless the neutrino masses are all degenerate and all offset from zero mass by a significant amount, which I think is becoming increasingly less likely given the rather stringent bounds we're getting on neutrino mass. So it's in my opinion that we effectively already know what the neutrino mass is, or at least we can guess what it is. If they're not degenerate, roughly that heavy neutrino mass eigenvalue is the square root of the atmospheric neutrino mass squared splitting, so of order 0.05 electron volts. If we take that attitude that we know what the neutrino mass is, then the measurement, quote unquote, of the sum of the like neutrino masses in, for example, the CMB data is tantamount to a detection of the relic background. And of course, also telling you something about the energy spectrum of those neutrinos. Now, it's that energy spectrum of the neutrinos which is very sensitive to a lot of physics in the weakly interacting sector that we may not understand in the early universe. Next slide, please.
Okay.
So, as I said, at least one of the neutrino mass eigenvalues, and if you think about the splitting, it's either the third one or number 2, depending on how you label it in the inverted, normal or inverted mass hierarchy. So at least one of those mass eigenvalues is bigger than or about the same as the square root of the mass squared splitting for the atmospheric neutrino, so 0.05 electron volts. So here you see the normal mass hierarchy and inverted mass hierarchy. So in the normal mass hierarchy, we've only got one of those neutrinos up there at that higher mass, and the other ones, nu1 and nu2, are presumably pretty light. So we'd expect the sum of the light neutrino masses with black body, thermal, Fermi-Dirac shaped energy spectra, we expect that sum of the light neutrino masses to be something like 0.05 electron volts. In the inverted mass hierarchy, of course, you've got 2 neutrinos up at that higher mass, and so you expect the sum to be about twice that, about 0.1 eV. So 0.1 eV is the figure of merit. If we wanted, for example, with the CMB and large-scale structure data, to distinguish between the hierarchies, which is a real possibility that can be done, then the figure of merit we're after is a sensitivity that's of order 0.1 electron volts. Now, it's interesting, if I look at the Planck paper, there are many ways, of course, you can cut the data and analyze it. But I think straight up, if we don't put any priors in it and just use the data that's indicated Planck and the polarization WMAP data and the high wave number data and baryon acoustic oscillations, then at 95% confidence, Planck gets a significantly tighter constraint on the masses than the previous experiments had done. And you can see that we're in that ballpark. We're getting down there. Next slide, please. So if I look at, this is a table from a paper which has about 50 authors on it from a conference, a workshop at the University of Washington a few years ago on trying to get at neutrino rest mass. And this is an interesting table because it gives the various kinds of probes that one might think of. In the second column, it gives the current constraint as of a few years ago on the sum of the light neutrino masses, and then also the potential reach of these probes, how well they could possibly do in the future, and it gives systematics and whatnot. So if you glance down this table, you'll see that lensing, weak lensing of the cosmic microwave background radiation, which is certainly going to happen. And you can see that the claim is that we can get down in this regime of something of order 0.05 electron volts, which would be adequate to distinguish this hierarchy. But keep in mind also what I said, that detection of that sum of the light neutrino masses is also tantamount to a detection of that relic background. So, you know, if we were to measure, for example, that the sum was 0.1 electron volts, that's interesting. It probably tells us we've got the inverted mass hierarchy. It also probably tells us that we've got, indeed, pristine, more or less vanilla, black body Fermi-Dirac energy spectra for those neutrinos. Next slide, please. Okay, so one thing that the experiments have established is that neutrinos have non-zero rest masses. Not terribly surprising, but now it's an experimental fact, and you can't turn away from it. And that fact immediately begs a question. The question is, once neutrinos have mass, of course, you can think of Dirac neutrinos, that I can flip their spin, I can flip their handedness, and then you can produce potentially things that are called right-handed neutrinos, which the weak interaction doesn't see. These are so-called sterile neutrinos. It's one way to envision a sterile neutrino. There are many models that make them. And sterile is a misnomer because these neutrinos are not actually sterile. They can feel the world and interact with the world through their vacuum mixings with ordinary neutrinos. So, in fact, in many of these models, you can mix them at such a tiny level with active neutrinos that the effective coupling strength of the sterile states is tiny, so tiny that you can never probe it in an accelerator, for example, or in a reactor experiment. But cosmology is a different matter. Next slide, please. So right now, there are several experiments, and there's been a lot of talk about this over the last year. A number of experiments that are suggesting possible interpretations involving sterile neutrinos. One of these, of course, is the mini boon experiment and its predecessors, Carmen and LSND. So they see an excess of electron flavor in a beam that's originally pure mu flavor. And one interpretation of the excess above background that they see is that a mu neutrino coherently turns into an electron neutrino via an intermediate sterile state. And because of the energy of those neutrinos and the baseline of these neutrinos, roughly the mass squared difference you would need to explain that is in the range of a few tenths of an electron volt to maybe tens of electron volts squared, something like that. Now that signal, if you combine LSND and mini boon, is my understanding, I'm talking to Bill Lewis, is now about 5 sigma above background, although it's not clear just exactly what that background is and how to interpret that excess. Okay, so interestingly, there's also a neutrino and source disappearance issue. There seems to be a deficit of electron antineutrinos coming from nuclear reactors or in the gallium disappearance experiment, for example. And if you look at I believe it's about 7% lower, the signal, than what's expected. And again, it's interesting that you can use the mixing parameters, oscillation parameters implied by the mini-boon experiment. It seems to be quite consistent with explaining the reactor anomaly. And of course, there was a lot of excitement over the last year because the early CMB observations seemed to suggest that, or at least in some people's view, it seemed to suggest that N effective was larger than 3, which I never bought. Anyway, next slide, please. I apologize for this slide. There were animations that make it not look quite so bad, but let me walk you through it. The point is that if sterile neutrinos exist, we have little or no idea. There's no good physics explanation or prediction for what their masses in mixing should be. In particle physics, the kind of old and our original ideas about how to think about this was the seesaw model, where sterile neutrinos would be at very high masses, maybe unification scale masses, with small mixings, and at those mass scales, God's in his heaven and all is right with the world, so to speak. The neutrinos, those sterile neutrinos, don't show up in astrophysics, and they don't show up in the laboratory. And they more or less explain also why the active neutrinos are so light. But there are many models other than that model, and there's no good reason to pick one over the other. And so the truth is, we really don't have any idea what the scale of the sterile neutrino masses is, or what their mixings are with active neutrinos. So on this plot is simply a cartoon. This is not a constraint plot. This is a cartoon that shows you what various kinds of sterile neutrino masses and effective interaction strengths, what regimes in astrophysics they would affect, and what kinds of probes of those mixing parameters and masses we can get from either astrophysics or the lab. So on the vertical axis is the rest mass of some sterile neutrino, going from of order electron volts to GeVs, and on the horizontal axis is the effective sterile neutrino interaction strength relative to the normal weak interaction. So on the far right-hand side is 1, so that would be a sterile neutrino that has normal weak interactions, like ordinary neutrinos. And on the far left-hand side is 10 to the minus 15. So that would be a sterile neutrino that would interact with an interaction strength 15 orders of magnitude smaller than the ordinary weak interaction. So if you look at this, there are some broad regions. So obviously the thing we're interested in for the CMB experiments in Planck is in the lower right-hand corner, masses of order an electron volt. And masses like that and fairly significant mixing affect Big Bang nucleosynthesis. They affect supernova nucleosynthesis. They can be probed by accelerators and reactors, as I just showed you. And I say here that they can be probed by 30-meter telescopes. Well, I'm from the University of California, so I'm plugging 30-meter telescopes. That's why that's on there. But the point is that abundances of the elements are sensitive to mixing between active and sterile species. And so to the extent that we can measure more confidently with higher precision light element abundances, that can constitute a probe. And obviously ineffective is a probe as well. Masses of sterile neutrinos of order KeVs to MeVs, these things make very interesting, excellent cold dark matter candidates. They can also be warm dark matter. Those neutrinos are not probed by the CMB. However, they are probed by X-ray astronomy, and our best constraints on those models come from X-ray astronomy. However, some models can evade all the X-ray constraints. And disturbingly, the models that make those neutrinos also produce them typically without thermal energy spectra. So that's an interesting point, is that the sterile neutrinos we're talking about and looking for here may not have the thermal Fermi-Dirac blackbody energy spectra. Finally, very high energy neutrino or higher mass neutrinos can be probed with the Fermi Gamma Ray Observatory, for example, and also those can affect nucleosynthesis, as I'll show you in a minute. On the right-hand side of this plot, I've showed you that these sterile neutrinos, generally, if you can produce them in astrophysics, they have some interaction, some handle on them, some mixing with active species, and it's kind of live by the sword, die by the sword. If they can get produced in astrophysics, they can also decay through that interaction. And so what I've shown you here are several different decay channels. So every neutrino can have that, every sterile neutrino that I've written down here can have the kind of decay into a photon that I indicate in the lower right-hand corner. As the sterile neutrino mass increases, and you can access higher threshold decays as shown. So the ones that have masses of hundreds of MeV or GeVs can decay through pions. I've shown the pi naught decay, but they can also decay through charged pions. Next slide, please. So now let's talk about ineffective as a probe of the neutrino sector. Next slide, please. So it's important here to say what ineffective really is. So the radiation energy density at photon decoupling is parameterized by this thing, which unfortunately is called the effective number of neutrino degrees of freedom. It is not. It is in fact a parameter, just a parameterization of all of the relativistic energy density that's extant at the photon decoupling epoch. And it's important to realize that this number is tagged to the photon decoupling epoch. It's not the number that's relevant during Big Bang nucleosynthesis. Okay? So I'll give you here the relationship between the radiation energy density that the CMB experiment will access and the photon temperature which they measure. And so that's what the definition of ineffective is. Now, if we ask what the standard model value is, it's there in yellow. It's 3.05 roughly. And why isn't that just 3 for 3 Fermi-Dirac blackbody neutrino spectra? And the reason, of course, is that when the electron-positron pairs annihilate, they can sometimes produce neutrino-antineutrino pairs, and those pairs will have energy so low that they don't thermalize. And so there's some extra energy density, decoupled energy density from that process, and so it's 3.05. So I give you here the previous measurements. You can see that the error bars are quite large. And there's one of Planck's results. Again, you can cut this many ways, but this is the one that's most interesting to me. And the thing that strikes me in looking at this is that all of these measurements are completely consistent with the standard model value. There's no evidence whatsoever for any extra energy density beyond that predicted in the standard model. Okay. Interestingly, one way that Planck can cut this is with the BAO data and stipulating that the sterile neutrino mass is less than 10 electron volts and has a thermal energy spectrum. Then you can put constraints on the existence of that sterile by using the mass and ineffective as shown. Next slide, please. So let me give you a couple of caveats on the CMB as a probe of sterile neutrinos. Remember, there are scenarios where the sterile neutrinos would not have thermal energy spectra and or number densities. So you have to be very careful here. When you try to connect Big Bang nucleosynthesis and CMB constraints, especially for helium-4, watch out, because ineffective is not what determines the helium-4 abundance in Big Bang nucleosynthesis. Remember, ineffective is that number that goes with photon decoupling. What determines the helium-4 abundance in Big Bang nucleosynthesis is really the ratio of neutrons to protons at roughly that freeze-out temperature that's of order 1 to 1/10 of a million electron volts, something like that. And in turn, that neutron to proton ratio is set by the competition of these weak interactions here in the lower left. Electron neutrino capture on neutrons to make protons, Dewey bar capture on protons, et cetera, et cetera. It's really the competition between those processes and the reverse processes that set the neutron to proton ratio, which sets the helium-4 abundance. And I'll point out that those processes, the rates of those processes, are very sensitive to what the neutrino energy spectra are. So that if there are active sterile neutrino oscillations, for example, that leave small distortions in the electron neutrino or electron antineutrino energy spectra, then that will affect the neutron to proton ratio. That physics is not ineffective. Next slide, please. Now this slide just shows you that these weak interaction rates are important in Big Bang nucleosynthesis. They vary over orders of magnitude. By the way, this is also tantamount to a detection of the relic background at the time of Big Bang nucleosynthesis. If we didn't put these weak interaction rates in involving neutrinos, we wouldn't get the right answer. Next slide, please. Here's the right answer. Standard Big Bang nucleosynthesis. It's plotted in the usual way. It's a tremendous success story, as you can see, for deuterium, and helium-4 is possibly a success story, very likely. Lithium-7 is not. Next slide, please. This is where we stand with observationally determined light element abundances. Deuterium is tremendous. It's fantastic. Helium is historically problematic because historically we've gotten it from a linear regression with compact blue galaxies, looking at H2 regions in those systems, and looking for a zero metallicity intercept. And the statistical errors are tiny, but the systematic errors are fairly significant. Planck's measurement is very good, in my opinion. And if I look at their measurement full up without at 1 sigma roughly, and look at 4 helium alone, then it's actually quite good. It's very interesting from a Big Bang nucleosynthesis standpoint. However, I'll caution you that this is very tricky, and the Planck paper is at pains to point this out, that there's a near degeneracy between N effective and helium-4. Of course, the reason for that is that both are quite sensitive to the ratio of the photon mean free path to the sound, essentially the sound horizon. And think about it, putting baryons in, making them neutrons and sticking them in alpha particles means that there are fewer protons, meaning there are fewer electrons, meaning a longer photon mean free path. That's right. Lithium is a mess. Next slide, please.
You're almost out of time, George, just to let you know.
Okay. I'm going to skip something here then pretty quickly. So sterile neutrinos can decay, and they can affect nucleosynthesis and ineffective, and that can lead to constraints. So I'll spare you the details on this, but let's just look at what sterile neutrino decay can do. Next slide, please.
Okay.
And let's go to the next slide after that. So this slide shows that sterile neutrinos can decay. Yes, that slide. So this slide shows that sterile neutrinos can decay into pions, as I showed you. The pions can decay, and eventually these decays lead to photons and neutrinos, extraneutrinos. Some of the photons, of course, always thermalize and dump their entropy into the plasma, which the decoupled neutrinos will not share in, as I showed you. And the neutrinos that are produced in these decays may or may not thermalize. Next slide, please. So just to show you what can happen, here's a sterile neutrino case that has a rest mass of 275 million electron volts, a very long lifetime. So this corresponds to a mixing angle so small, we could never measure this in a laboratory. But you can see this plots entropy versus photon temperature decreasing to the right. As the universe expands, the temperature goes down. And the decays actually generate all the entropy in the universe, or 95% of it in this case. They would have to. Next slide, please. So all that entropy generation dilutes the active neutrinos and cools them. That's the red curve shown here in a temperature plot. Next slide, please. So the bottom line is this. If you look at this calculation, for example, with that neutrino I showed you and a bunch of other neutrinos, so these are plots of sterile neutrino rest mass on the vertical axes and some kind of mixing of, some measure of the mixing with active neutrinos on the horizontal axes, and these are contours of ineffective. And this comes from these two processes of sterile neutrino decaying into photons, which causes dilution and reduces ineffective, and also decoupled neutrinos, which actually add to ineffective. So in some cases, you get dramatically huge values of ineffective, like 5 or 20. Other cases, you get very low values of ineffective, like 1. So I can look at this plot and see immediately from the Planck results that I can eliminate big areas of sterile neutrino parameter space that I could never probe in a laboratory. That's very interesting. Next slide, please, which is the summary slide. So ineffective constraints from the CMB do not completely, at the current time, rule out the light sterile neutrinos hinted at by the experiments, but they certainly greatly pressure that interpretation of the data. They do rule out an awful lot of parameter space associated with heavier sterile neutrinos with tiny mixing angles that we can't probe in the lab. I think this is extremely interesting. They do not constrain sterile neutrino dark matter models as of yet, although some of those models actually have interesting predictions about dilution, for example, that might show up eventually. So I think ineffective together with the sum of the light neutrino masses is a fantastic probe of the physics of the early universe. It's more than complementary to laboratory probes. It goes way beyond them. And I think this probe will only get better with time. Thank you.
So thank you. Questions, please.
Yeah, high energy physicists often talk about Majorana neutrinos, and astronomers never do. Could you sort of shed some light on what the differences are and so forth?
So the question was about Majorana neutrinos and the astrophysics perspective on them.
Well, we don't know whether neutrinos are Majorana or Dirac. So remember that if we consider let's just consider for a second a massless neutrino, a massless neutrino. Remember that the weak interaction only effectively couples to left-handed neutrinos and right-handed antineutrinos. So if I took a ordinary neutrino that was left-handed and I somehow cranked its spin around and forced its spin to point along its propagation direction so it was right-handed, I could ask myself this question: what is that neutrino? Is that right-handed neutrino the same as the antineutrino? If the answer is yes, that's a Majorana neutrino. If the answer is no, it's a right-handed neutrino that doesn't couple the weak interaction, then we call that thing a Dirac neutrino. The original neutrino is called a Dirac neutrino. In fact, the usual way the seesaw model is envisioned is you start with something like a primitive Dirac neutrino and then take the sterile pieces and put them together to make a Majorana part, a set of Majorana neutrinos, and take the active pieces and put them together to make a set of Majorana active neutrinos. So the basic answer to your question is that so far, everything I talked about and everything we can probe with neutrinos is not sensitive to whether they are Majorana or Dirac, except insofar as there may be that physics essentially might imply that there could be sterile states, as I discussed.
Okay, thank you. One last question.
George, your first point on this last screen is that CMB basically rules out these light sterile neutrinos that we would like to see in experiments. But now suppose that the linear theory of structure formation does not hold. Does it give new hope for these reactor experiment people?
Did you get it?
No.
Okay.
I'm sorry.
I try to. Imagine that linear structure formation theory does not hold. Is there new hope for the high neutrino masses found or indicated by reactor experiments?
Yeah, I think what we know right now, as I pointed out, does not actually constrain all of that parameter space that would explain, for example, mini-boon and reactor disappearance experiments. I presume that the CMB data and the analyses will get better with time, and I think you've been discussing that. So maybe they will put more pressure on these things, but right now I can't rule them out. I think if your question is, are there going to be surprises with structure formation and neutrinos, I'm not quite sure how to answer that. We don't know, of course, what the dark matter is. Something like WIMPs, of course, they have an incredibly tiny collisionless damping scale, Sterile neutrino dark matter may or may not. I mean, some of it, in some models, it can be very cold dark matter. And in other models, it can look warmish. And if it's warmish, then of course that will show up in some way. Is that the question you're asking?
Yes.
Probably yes, but the time is over. We thank you again. Thank you very much for this difficult talk, technically.
Thank you.